Hello everyone, welcome back to Math with Allison. Today we're continuing our series on integration, so we're going to go into some basic rules. So let's go ahead and dive into it. We have an example here, the integral of 3x squared dx. So if we want to set this up in a way that makes a bit more sense to us, we can think of it as taking the derivative of something, that's going to be our solution, is equal to 3x squared. So in our case, that's going to be the derivative of x to the power of 3. So that's almost our full solution. The issue is that there could possibly be a constant because the derivative of a constant just goes to 0. So this could be any number right here. So we just have to make sure to account for that. So what would happen if it was just the integral of x squared dx? We don't have that 3 in front. That leads us to the power rule. So let's go ahead and talk about what that means. We know the derivative using power rule is where we bring down that exponent and then subtract 1. So like we talk about, integration or antiderivatives is just working backwards. So instead of subtracting 1 from the exponent, we're going to add 1. And what we do is we divide by that new exponent. And then, of course, we have that plus c value. So let's go ahead and see this in action. Here we have the integral of x squared dx. So we want to add 1 to our exponent and divide by that new exponent. Of course, you don't need to write 2 plus 1. You could just immediately go to this step where we write x cubed divided by 3 plus c. And that would be our solution. And I always suggest checking it to make sure it is for sure our answer. So we can check it by taking the derivative. So we have x cubed over 3 plus some constant c. And when we take the derivative, we bring down that power, and that becomes a 2 divided by 3 plus 0. And here we can see we just get x squared. And what we're checking is that this, our solution right here, matches with what we're integrating. If it matches, then we're good to go. So let's move into some other rules here. Here we have the constant multiple rule. So let's talk about what that meant with derivatives. When we take the derivative of a constant multiplied by our function, that meant that we could take out that constant and just take the derivative of whatever our function is. So when it comes to integrating, we can do that exact same rule. We can take out the constant and then integrate the function. So let's see what that looks like in action. Here we have the integral of 3x to the power of 6. So what we're going to go ahead and do is bring out that 3, and then we have the integral of x to the power of 6 dx. So now we can use that rule that we just learned. So the 3 stays out front, and now we can use power rule. So I add 1 to the exponent. 6 plus 1 is equal to 7. I divide by that new exponent, and then I add on some constant c. And this right here is our final solution. Let's go ahead and check it. Take the derivative of, I'll write that as 3x to the power of 7 divided by 7 plus some constant c. When I take the derivative, I have 3 times 7x to the power of 6 divided by 7 plus 0. And here we get 3x to the power of 6. And now I can tell that these match, this one right here and what we were originally integrating. So we know that that is our final solution. Next, we have the sum and difference rule. So when it comes to differentiating, this meant that we can distribute that derivative across the plus and the minus. So we could take the derivative of each part individually. We can do the same thing with integration. So this just means when I split it up, I have the integral of f of x, the first function, in terms of x, plus or minus the integral of g of x in terms of x. So notice here you have to complete the sentence of both of them. So we have the integral and dx and the integral and dx. And this is separate from the plus and minus. So make sure you have that notation. Let's go ahead and see this in action. I want to take the integral of x plus 2x squared. So I'm going to use our sum and difference rule. So I get x dx plus the integral of 2x squared dx. So first, let's go ahead and take out this constant right here, this 2. So we can use the constant multiple rule. And now we can actually take the antiderivative. So remember that when there's no exponent, there's a secret exponent of 1. And so here we add 1 to the exponent, so we get x squared, and we divide by the new exponent. That 2 hangs out here, and now we have x to the power of 3 divided by 3. And then don't forget to add that value c. So if you wanted, you could rewrite that. So that becomes x squared divided by 2 plus 2x cubed divided by 3 plus c. So let's go ahead and check it out to make sure this is actually our final solution. When we do that, we bring down that power and subtract 1 from it, and then all the scalars remain the same. So that simplifies out to those divide out x plus 2x squared. And of course, we want to make sure that matches. So this, of course, matches with what we were originally integrating. So we are good to go. That's our solution. We have one more basic rule here. We want to take the integral of a constant. So let's talk about the derivative of a constant. Like pretend we're taking the derivative of 2. The derivative of 2 is equal to 0. And remember, this is because we can rewrite it as k times 1. And that 1 can be rewritten as x to the power of 0. So now what we are going to use is power rule. So that k hangs out, and we are just taking the derivative of x to the power of 0. So when we do that, we're going to go ahead and use power rule. So I bring down that power, and I subtract 1. But notice here, we are multiplying by 0, and when you multiply by 0, you just end up getting 0. We are actually going to use the same trick for integration. So let's go ahead and rewrite this as k times x to the power of 0. So now we can go ahead and bring out that constant using the constant multiple rule, and we can use power rule now to take that antiderivative. So we add 1 to the exponent, and we divide by that new exponent, and don't forget to add c. So let's go ahead and rewrite this. This just becomes kx plus c. So basically, when you integrate a constant, I'll just give a little example right here, 2 dx, you just tack on an x, and don't forget your c. So let's go ahead and see some fun examples. Here we want to take this entire antiderivative, and I'm going to show all the steps. You do not need to show all the steps. I just want to work through them. So first, we have the integral of 3x squared dx, and now we're going to add the integral of 2 dx. And don't forget, now we're subtracting 5 times the square root of x dx. So now what I'm going to go ahead and do is use the constant multiple rule. So I'm going to go ahead and bring out all of these constants. This square root of x, I'm going to go ahead and rewrite that as x to the 1/2 because we can apply power rule. So let's go ahead and do that for all of these. So first I add 1 to the exponent, and I divide by that new exponent. This becomes a 2x, just like we talked about. And then right here, we add 1 to the exponent. So 1/2 plus 1 is equal to 3/2. So x is the 3/2, and we divide by 3/2. And then finally, we add on that value of c. So we can go ahead and simplify this out a little bit. These 3's cancel, so we just have x cubed. So when we divide by a fraction, we can actually just multiply it by the reciprocal. So that becomes 5 times 2/3 x to the 3/2 plus c. If you wanted to keep simplifying, you could. I would say if I was the one grading this, I would be perfectly fine by it. But, to each their own. And plus c. Okay, that looks pretty dang good. Let's go ahead and try one more. So here we have a fraction. We don't know how to integrate fractions yet. So instead, what we're going to do is simplify it. So first, let's go ahead and rewrite this as 2 fractions. First, we have 4x to the power of 19 divided by x squared minus 5x to the negative 8 divided by x squared dx. Now we can go ahead and simplify both of these. So this 4x to the power of 17, I just went ahead and subtracted their exponents. And now right here, we have a negative exponent, which actually means we get to move it to the bottom. And so this 5 remains in the numerator, and we get x to the power of 10 because 2 plus 8 is equal to 10. So now that we have this pretty much simplified, we can go ahead and use our integration rules. So first, I'm going to go ahead and split this up. And I'm going to go ahead and use the scalar multiple rule. So I'm going to bring out those scalars. And I'm going to go ahead and write this x to the power of 10 as x to the negative 10 if I bring that up. That way we can go ahead and use power rule, right? So let's go ahead and do this thing. I get 4 times x to the power of 18 divided by 18 minus 5. And now I get x to the power of negative 9. I can do math. Negative 9 plus c. So we could go ahead and simplify this. So a 2 cancels out of both of these, and I have a 9. So this becomes 2x to the power of 18 divided by 9. And now this becomes a plus 5, and then we can move that x to the bottom. So that becomes a 9x to the power of 9 plus c. And that is our final solution. So notice how much algebra is involved. We actually didn't do any calculus until we got to this step right here when we actually took the antiderivatives. That was the only calculus step, actually. The rest of this is simply just algebra. So algebra is a really good tool to have in your back pocket. But that is all I have for us today. If you enjoyed this video, please give it a thumbs up. I have many more videos like this, so make sure to check out my playlist. They're linked down below. Otherwise, thanks for watching.